Hi everyone. This is part 2 on solving systems by elimination. And what we said in part 1 is that you can solve by elimination as long as one of the variables matches up. And what I mean by that is like if you have a 2x and a negative 2x in your equations, you add them up and they're gone. Or if you have a 5y and another 5y, you subtract them and you're gone. But what we want to talk about today is how you can still use elimination if you don't have that perfect match. And the way you do it is by taking one of the equations and multiplying it by a certain number. It'll be different for each problem, but you multiply one or possibly both equations by something to create that match. And the reason you're allowed to do that is because what you're doing, when I say like multiply an equation by 2 or multiply an equation by 5, what we're really doing is we're taking the equation and we're multiplying both sides by 2, or we're multiplying both sides by 5, which is one of the things we're allowed to do when you're solving equations. So what I'm going to say is, instead of saying like I'm going to take this equation and multiply both sides by 5, I'm going to say let's just multiply the equation by 5. And I mean go through and just multiply each part of the equation by 5, or whatever the number is, which is something you guys are allowed to do. So let's look at this problem here. Let's say I asked you to solve this system here, 2x minus 3y equals 4, and x plus 4y equals 13. And you look at it and you go, well, it doesn't have a match right off the bat. You know, I don't have that perfect match. I have a 2x and an x, I have a negative 3y and a positive 4y. Nothing's going to cancel if I add or subtract these equations if I try to do it by elimination. But if I take that bottom equation and I multiply it by negative 2, it would have a perfect match. And remember, what I'm really doing is I'm taking that equation and I'm multiplying both sides of it by negative 2, which is something I'm allowed to do. So let's do this. Let's just turn this into an example and solve this exact equation, or this exact system of equations. So I look at the problem and I realize, okay, I want to solve by elimination. I don't have a perfect match, but I can get there. And I said the way I'm going to get there is by multiplying the bottom equation by negative 2. And basically creating a new system of equations. So let's do that. I'll write it next to it actually, just to save a little space for the work. I'm going to leave the first equation, 2x minus 3y equals 4. And I'm going to take the bottom equation, I'm going to multiply each part times negative 2, kind of like a big distributive property. Negative 2 times x is negative 2x. Negative 2 times 4y is negative 8y. Leave the equal sign. And negative 2 times 13 would be negative 26. Now I'm going to do the elimination part. See, I created that perfect match so that if I add these two equations, the x parts cancel. 2x and negative 2x is gone. And then I can solve for y. So when I finish adding, negative 3y and negative 8y would give me negative 11y. And a positive 4 and a negative 26 would give me negative 22. I finish solving for y by dividing by negative 11 to cancel out that negative 11. And we get positive 2. Negative divided by negative is positive. 22 divided by 11 is 2. So the first half of my answer is 2. Now what I want to do is go back, pick an equation from the original problem, and remember it really doesn't matter which one you choose. I'll just take the bottom equation and I'm going to substitute 2 for y right here. So if I do that, I will have x plus 4 times 2 equals 13. I took that bottom equation, substituted 2 for y. 4 times 2 is 8. So I get x plus 8 equals 13. And then I only have one step left. To finish solving for x, I just subtract 8 from each side. And x equals 5. So final answer is always x first and then y. 5, 2. We'll write it as a point. Final answer 5, 2. So we had that extra step at the beginning of the question where I wanted to solve by elimination, but I didn't have a perfect match. So I multiplied the bottom equation by -2, which gave me the perfect match, and then basically it turned into a 7.3 question. It was add the equations to eliminate x, solve for y, plug it in to get x. All right. So we've been talking this chapter, or this module, about special cases, like when there are no solutions or infinitely many solutions. We saw it when we talked about graphing, but now we want to talk about it algebraically, or working through equations. Now those two special cases happen when you go to eliminate either the x or the y, and what you notice is that both variables get canceled out. It's going to be one of those two special cases, and it depends on what's left over. So if you're going to eliminate either the x or the y, and you notice that the x's and y's all cancel out, if what's left over is a false equation, like 5 equals 10, or -7 equals 12, or anything that actually is not equal, then that means there's no solutions. And this is the algebraic version of when you had parallel lines that never cross, and we called that no solutions also. Now, if all the variables cancel and you get a true statement, like 10 equals 10, or -2 equals -2, or something like that, then what you get is infinitely many solutions. And this is the algebraic version of when you have two lines, but they're actually the same line on top of each other. You have one line here, and the other one is actually the exact same equation on top of it. So let's do one more example. We're going to solve by elimination again. And what you notice in this question is not only do we not have a good first step here, not only do you not have a good match, I should say, like you can't just add and cancel, but you can't even do it in one. Like there's no way I can multiply one equation to make a match. We have a 2 and a 3 on the x's, we have a 6 and a 9 on the y's. So what I'm going to do is I'm going to multiply both of them. Let's try to make these x's match up with a 6. So I'm going to do this. I'm going to take the top equation and I'm going to multiply it by 3. That would give me a positive 6x when I do that. Then I'm going to multiply the bottom equation by 2. That would give me a negative 6x. So remember on the first slide today I said sometimes you have to multiply one or both equations by a number to get that perfect match. This is one where you couldn't do the perfect match with just one multiplication. So let's see what we get here. We're going to do kind of a, think of it as a big distributive property again. Take the first equation, multiply everything by 3. 2x times 3 is 6x. Negative 6y times 3 would be negative 18y equals, and then 3 times 4 is 12. Now let's take the bottom equation, multiply everything by 2. 2 times negative 3 is negative 6x. There's that perfect match that we created by multiplying by a 3 and a 2. 2 times 9y would be positive 18y. And 2 times 6 is 12. Now when you add the equations, remember this is what we were trying to do, is cancel out the x's. But what happened is we also cancel out the y's. Negative 18 and a positive 18y also cancel. If everything cancels, it leaves a 0. Now on the other side, remember we're adding here, those don't cancel. That's not a 12 and a negative 12. It's a 12 plus 12 is 24. Now as soon as the x's and y's canceled, I knew that the answer was either going to be no solutions or infinitely many solutions, automatically. If I had gotten the same number, like 0 equals 0, then I would say infinitely many solutions. Since I didn't, since I got a false statement, 0 equals 24, the answer to this question is no solutions. And that's it. There's no more work. Once you realize it's one of those special cases, it's actually less work. When the x and the y both cancel out, you're done with the question. You just got to make sure you know which one it is. Is it no solutions? or is it infinitely many solutions?